Our speaker tonight has spoken at hundreds of events on big data, and performance, and scalability, has authored numerous articles and books, and has 20+ years of experience. Please welcome the CEO and CTO of CodeFutures, Cory Isaacson.
Thanks, everyone. So, I got to turn it on again. Can you hear me okay? Is that coming across? Okay. Anyway, nice to meet everybody. It's a great crowd we have tonight. So, and I see you're all really noisy, so that's good. I'd like to keep it interactive. You know, I don't like it to be boring where I just talk and talk and talk and everyone falls asleep, so we'll keep it alive. And if you have questions as I go, I'm happy to take them. So I'm going to talk to you about big data and scalability. So how many of you have ever, well, first of all, how many of you work with databases? Oh, good. A lot of you. I hope that's good. Who's actually seen a database performance problem in their career? That's a loaded question, right? If you said no, then I tell you that I have to do a completely different seminar. So I just want to talk to you about scaling big data, of course, is a big issue today, right? We all have databases that get slow. We have to be able to figure out how to overcome that. It's a lot of work. Many of you may have noticed that there's a lot of technologies. I think there's something like 250 new database engines that have been introduced in the last few years. So it's quite an array of technologies to choose from. It's getting more and more, crowded the field every day, and so there's a lot of choices. But in working with databases for my entire career, we actually started looking at it with my team over the last year. And we actually looked at it and we said, maybe we've been actually looking at the problem wrong the whole time. And so I'm going to be covering that and what kind of concepts we mean by that, and see if we can look at the problem a different way and make things a lot easier and a lot faster and a lot more scalable in a much simpler fashion. So that's what we're going to be covering at the end of the talk. So Eric told you a little bit about me. I have a couple of books that I wrote. I've written a lot of articles. The latest one is called Understanding Big Data Scalability. It's an ebook from Prentice Hall. You can find it on Amazon. And I thought I would ask one more trivia question. We'll see if you can do it. So we also are makers of products at our company. We have a product called DB Shards, which is for scaling MySQL. But we're working on a new product now called Agile Data. And that's going to be coming out probably early next year. And so because it's Agile, I had an Agile trivia question, and Eric thought it was so hard that he took it off the list. So the question is that if you look at Agile process, an Agile development process, there are two roles, and it's called the chicken and the pig. So who knows why they got those names? Anybody know?
Chicken legs eggs and the pig is bacon.
And what does that mean?
The pig is invested more than the chicken.
Yeah, that's right. The pig is, so for that, if you give me your email afterwards, you get a free book. So what I want to cover tonight is I'm trying to provide, I hope, practical information that you can actually use right away. So hopefully you can find some benefit out of this. And again, if you have questions as I go through it, I'm happy to take them. And then at the end, we'll have time for more questions as well. So we're going to talk about scaling big data, the fundamentals. Again, have we been looking at databases the wrong way? And we're going to talk about a new concept called an Agile view of big data. So has anybody ever noticed that databases are very hard to make flexible, especially if you have a big database? Anybody ever tried, for instance, just to do an alter table on a 5 terabyte database or something like that, or a huge table? Has anybody seen that? Could take a long time, right? Hours, could even take days, right? So we're working on concepts to try and make big data much more agile, much more scalable, in a much more flexible manner, and that's what we'll be talking about toward the end of the talk tonight. So if we're talking about big data, there's a lot of definitions about big data. We talked about velocity and volume and variety, those kinds of things. But basically, I have a simpler definition that I like, which is if you have a problem with your database and it's growing, you have a big data problem. I think that qualifies as a definition. And if any of you have had performance problems where you have a lot of headaches, you have user complaints, those kinds of things, that's definitely a big data problem, especially if everybody's complaining and you're staying up all night or working all weekend, things like that, right? So we want to try and avoid that and have a better infrastructure to get around that. And so essentially it looks like this, right? You have an application, the database is too stressed out, can't do it on a single server anymore, and so the database starts to fracture. So And by the way, these pictures really are from my book, and basically I did all these sketches myself, so I want you to know that those original prints that you have are very limited. There's very few of them. Okay, so the one thing that we know about databases is what? They always get bigger, and when they get bigger, they always get slower. That's pretty much axiomatic, right? That's just the way that they work. And so we want to be able to see what we can do to get around those challenges, and obviously scaling is the way to do it. We're going to talk about different techniques, but first we're going to talk about some of the problems that actually lead to this. But the fact that we have big data, that data is growing, fine. But the other thing is, how can you actually get meaningful value out of it? Have any of you had so much data that it's really hard to get queries to run, and you can't really find things that you want, or you have a database where you can write to it a lot, but you can't really get the data out the way you want? Anybody ever seen that problem? So that's one thing that we're really going to talk about how to address, because a database to me is kind of like, remember when you were a kid and you had a closet that was really dirty and you just threw all kinds of stuff in it, and then you tried to find something a couple months later and it was impossible, right? So very often a big database ends up like that, where you basically can put a lot of data in and you write a lot of data, but you can't get the data out in a meaningful way. And that really cuts the value of the whole system down, and so you really want to be able to get around that problem. Now we know data is growing, but what surprised me is the rate that it's growing at. I think I read, I can't remember how much, does anybody know how much it is a day now that's being written in the world of data? I think I heard something like an exabyte or something. Anyway, it's gigantic what's happening right now. And the rate of data is increasing incredibly fast. And the reason is we have so many different sources. So it started out with things like social networks and search engines, but now we have mobile devices. Everybody's generating tons and tons of data from our mobile devices. All that data is being tracked somehow or another. If you use apps, most apps are tracking something. We have system data that's incredibly voluminous, that's coming out of different types of IT systems. And now we have this thing called the Internet of Things. So that's really growing as well. So now there are going to be things that are essentially, one of the architects on my team has this idea that he said that in the next 5 to 10 years, he believes that everything is going to have a CPU in it and a network connection. That's just the way it's going to be. If you look, for instance, at I actually heard this story. Does everyone know what the new Tesla cars are? You've seen those? They're really pretty cool. And apparently, the CEO of Tesla was actually giving a talk somewhere, and somebody heckled him about something about, the battery ran too low or something like that, whatever. And he actually went back and looked, and they actually had records of what actually happened with that car, because that car is feeding information. So they actually knew, and he said, no, it actually didn't happen that way. You didn't plug it in or whatever. So the point is that everything is going to be generating information. Cars, we're going to have things like wearables, health monitoring capability, all of these things are going to be generating data, and that's going to make this problem much, much worse. But it also means that we have phenomenal opportunities as IT professionals and database professionals to actually take advantage of this and conquer this problem. It's going to be very exciting for a long time. So we have a customer that we work with called Big Door. If any of you have ever been on NFL.com or Starbucks, any of you have been on those websites? Okay, so when you go on those websites, you know how you can earn loyalty points? Okay, anyway, I don't know if you've seen it or not, but anyway, the loyalty engine behind most big websites is Big Door. That's what they do. It's called gamification of websites. And they had a very interesting big data problem. And essentially when we came to them, what they were doing was they were collecting all these loyalty points, and that was working okay. They were using a single MySQL database and running in the cloud at Amazon. Obviously they needed to scale it. But the real problem that they had was fascinating, is that they basically wanted to put together a leaderboard of who were the top earners of points, let's say on NFL.com. And that was a very, very difficult, if you think about that, that's a very difficult problem, because you have to aggregate all the points, which are billions of different individual records. And then what you have to do is sort them, and let's say pick the top 100. So they needed that type of capability. So to do that, that was very, very challenging and difficult. And the way they were doing it at the time was that every 2 or 3 hours, they were actually doing this giant query in MySQL, taking the results out, putting it into a file, sorting it, and then sticking it back in another table, and then it would eventually show up. So what that meant was somewhere between 3 and 4 hours after the fact, you could actually see what your status was, if they only had 1 or 2 big customers. Well, they started to get a lot of other big customers, and that really wasn't going to work. So we're going to talk about later with this concept of an Agile big data infrastructure, how you can actually solve that problem in a real-time way. And we actually did that for them, and it's been working really, really well. And they've grown, I don't know, many, many times since that they had that set up, and it's working really, really well. So one thing we also know is that there's a joke that comes from the mainframe days, which is that all CPUs work and wait at exactly the same speed. So if you're going to make a CPU wait for I/O, it doesn't matter how fast that CPU is, it'll wait just as slowly as any other CPU, which means it's doing nothing while it's waiting. That's the point. That's the point. And so this is an actual graph from one of our other customers that basically showed that their database was performing so poorly that all of that red is I/O wait time for the CPU. So it's not doing anything during that period of time. And that little bit of blue on the bottom was the only productive user CPU that they had. And so this is a really bad problem. And when you see this, you know that you really have to address it quickly with your database. So you don't want this happening. You'd like to see a lot of user CPU and very little I/O wait. But this is a good example of what causes a database scalability or performance problem. And here's another graph about why databases slow down. Well, one thing we know is, like I said, is as the database gets bigger, it's going to get slower. But the thing is, it doesn't happen in a nice linear fashion. It happens in a curve that looks like this. And early on in my career, we actually had a company, a consulting company, and we actually wrote all the systems for Fox Television. We actually wrote, I think, one of the first integrated TV network systems in the world at the time. And they just called me recently and said the system had its 25th anniversary, so that'll give you an idea of when we did it. But anyway, it was a database-driven system, and it was all working fine for a couple of months. The first couple of months we launched it, and everybody was happy. And then one day we came in, and the performance was just, the response time just went out the roof, and all the users were calling us and complaining. And this was back then only 100 users around the country with, there was no internet or anything like that. So, but it was pretty horrific thing because it really was stopping everybody from doing work. And we're going to talk about why that actually happened. But the point is that that database, when it slowed down, it didn't slow down in a nice, predictable fashion. Literally, the day before it was totally fine. And the next day, people were getting 20, 30-second, 1-minute, 2-minute response times for getting things working. So you have to be careful that when you start to see this database slowdown occurring, you have to look at what's really causing it. So we're going to talk about some of the causes that lead to this, but this kind of thing is really not very pretty when it happens. Okay, so there are what we call enemies of database performance. And the first one is what? The table scan. Who's ever had a table scan where you're missing an index on a table? Okay, that's a very, very bad problem. As soon as you have that, you know you're going to have horrible performance. It's just axiomatic that that's going to occur. And so basically, that's what happened with that system at Fox. We actually had one table that was doing a table scan that was missing an index. And when that table got big enough that it wouldn't fit in memory anymore, all of a sudden the response time was 100 times slower. Because at that time, disks were not what they are today even, and they were very, very slow. And that's exactly what happened. So essentially what can happen is if you have non-tested queries, or you don't plan your indexing well, any of those kinds of things, then you can run into this problem. So that's what a table scan looks like, because basically what it means is you're no index, so you're going to read from the top of the table to the bottom and search everything in it. And anyway, it's about the most inefficient thing you can do with a database engine.
Could you do something with the mic? There's some sort of a feedback over our head.
Yeah.
So maybe just turn it off.
Okay.
Oh, okay. But that's just turning off the mic to fix the other thing. I mean, we can hear it. I mean,
Yeah, if I go like this, is it better?
no,
Is that worse?
We're guessing it needs to be
Just
balanced.
switch
Okay.
All
All right. Can you hear me without the mic? Yeah, speak loud. Let's do that. All right. So let me know if it's too quiet, and I'll see what I can do. All right. Okay. So So another image of this too is when you have table scans, this is something else I know, is that if you have one slow query and all your other queries are fast, you're going to slow down the entire response time of the whole system very often. Because a table scan in particular takes a huge amount of CPU and disk, and what it will do is slow down the I/O of the entire system just because you have one bad query. And so very often when we get a customer coming to us and saying, oh, we need to scale our database, we have to do this, we're having horrible performance, the first thing we advise them to do, even though we're in the business of scaling databases, is look at all your queries and find out what the slow one is, because probably you're just missing something simple that you can fix right away. So it's a very, very good technique to apply that. Okay, so enemy number 2 is concurrency contention. So this is somewhat similar, but this is basically comes from 2 users trying to do the same thing at the same time. And it usually is caused by a poor data model design. You have a data model that actually has too many users trying to do the same thing on the same table. So for example, has anybody ever had, let's say you're accumulating something every time a user actually does a transaction, and you put that in one row in one table? That's a very good example of a concurrency problem. So you don't want to architect something like that. It causes a lot of blocking. It can make your transactions too long. And also, though, is if you're using some of the more modern NoSQL engines, a lot of them are, or in-memory engines, a lot of them are single-threaded. If you looked at VaultDB or Redis, those products are actually single-threaded. And so if you have any one query that's actually going to take longer than a certain amount, you'll slow down everything else in the whole system. So you have to be very, very careful about that. So here's what concurrency contention looks like. You're basically, everybody's trying to write to one row in the same table. If you have too much of that, you're going to slow down everything. Again, a very common problem that we see when people come to us with performance problems. And it can also look like this, where you have requests that are just sitting there and waiting for that single-threaded engine. That's the same type of capability. All right. So an enemy number 3 is just slow writes. So writes are just going too slow. And so basically what causes that is generally that you have a large table that you have a lot of indexes on, and all those indexes have to be updated at the same time every time something's being written to that table. So if you look at this, essentially if you have, again, one write and a lot of indexes to update, what happens with indexes is, we talked about the different kinds of indexes, but basically what happens with indexes is they have to juggle everything when new data is going into the index. And so if you have a lot of them, they're all sorted different ways based on different values in the table, and it can really make a lot of computational processing requirements on the system. So it's a very, very common requirement. So a lot of people think that this only applies to the traditional relational databases, these problems. The truth is, it applies to all types of databases. You can make any of them slow if you do things the wrong way. For instance, if you look at some of the new SQL or NoSQL databases, how many people here work with MongoDB, for instance? Okay, how many people have noticed that over time, MongoDB is adding more and more features that are a lot more like MySQL was? They have transactions they're adding now, I heard. They have actual, they've added indexes. Now they have things like MapReduce processing. So they're adding more and more capabilities, which are going to push them more and more to the same type of problems that we've seen all along. So it's very interesting that I actually think that what you'll see is, over the next few years, a convergence of all these technologies, because I think the vendors will get pushed to do a lot of the same types of things over time. Why? Because how did Oracle or MySQL or any of these databases get all the features they had? Because somebody like us asked for them. It wasn't that the vendor just said, oh, I need to do that, right? They did it for some reason. So that will happen as well. So it's important to understand these because it applies to every type of database. So based on this, I came up with what I call the 3 laws of databases, which are essentially law number 1 is that small databases are really, really fast. Law number 2 is that big databases are really, really slow. And so the moral of the story is keep them small and everything is fine. That's what we want to do today. So, and it is actually true, and it does work quite well. So what is the answer? The answer is database sharding, right? Now, how many people have heard of vendors that have scalable databases and they say sharding is a bad idea. Okay, I guarantee you they're doing sharding underneath the covers. Right? They may not let you touch it, or may not give you access to it, but the same technique that I'm going to show you is actually what every single scalable database is doing. So I'll talk about what that technique is and how it actually works. So basically, this is from Wikipedia. This is a formal definition of database sharding. And so what they say is they say it's horizontal partitioning. It's a database design principle whereby the rows of the database table are held separately. So you're basically taking rows and you're spreading them across multiple machines to actually do it and put them on separate machines so they can all work in parallel. So it's a kind of a complicated technical definition. So I have a simpler one, which is you start with a big monolithic database, you break it into a bunch of small databases across many servers, and you use a shard key, meaning you're doing it by some sort of value. That's how it works. Now, you'll see that there's different kinds of sharding. I'll talk about it in different kinds of techniques. But any data engine you have, or any database you run into that's scaling across multiple nodes, is splitting the data by some sort of key, and it's taking basically those values and putting it across the network. There isn't really any other way to do it. So the fact that people say sharding is not good or whatever is more marketing than anything else. The truth is Google popularized the term a long, long time ago, and it's been working for them pretty well for a very long time. I'd say Google's doing pretty well on this score. All right, so the key to database sharding is one thing, which is share nothing. So if any of you, how many of you have studied anything about parallel computing? Okay, so the one thing you have to do to make parallel computing go really, really fast is to have a share nothing environment. It's called Amdahl's law. And if you study that, you know what I'm talking about. That's what it is. It's if you have any shared component or any centralized component, it's going to limit the throughput of your system. So it's very, very important that you actually get things to run across multiple servers that are all independent. And that's what you really want. And when you do that, you get awesome capabilities. So what does it look like? Sharding infrastructure, typically you have an application server, you have client machines, client drivers, and essentially what's happening is you're writing to these different servers and you basically partition the data. Let's say this one example is by customer ID, and essentially you're sharding the different customers across different servers. That's a very, very well-known technique. Early on in our company, we actually ended up supporting a lot of game developers, so I'll be talking some more about some game applications. So Big Door is kind of like that, but also real player games that people have in Facebook and other places. And almost all games are sharded by what? Player ID. You see that's very, very common. Very, very common when we do it. So what do you want when you're doing sharding? You should have linear scalability. If you have a share nothing environment and you actually are adding servers, if you add servers, you should be able to see exactly the same performance in multiple. So this was an actual MySQL write test. This is actually years and years old, but it still holds pretty true on Amazon EC2. And you can see that we went from about a little over 2,000 transactions per second all the way up to 10,000 when we went from one shard to 4 shards. So if you do it right and you have a shared nothing environment, that's exactly what you should get. You should get linear scalability. Now, how many of you have worked with a scalable database that doesn't scale at 100% per node? Anybody seen that? Okay, it's very, very common, right? And that's because most of them have something that isn't shared nothing. If they really had it in a shared nothing way, and I'll show you what makes it shared nothing, and I'll show you what makes it not shared nothing, and you'll see exactly what the drawbacks are of the second approach. Yes?
So effectively, haven't you just transferred your problem to the network guys? And when the network gets overloaded?
Yeah. The question is, if you can't hear it in the back, is haven't you just transferred the problem to the network so that the network is getting overloaded? And the truth is that the limitation in its distributed system is the network. And I'm going to show you exactly where it's pretty effective and where it gets less and less effective. But that is one of the problems, is that you don't want to have to do too much network, or you do start to ruin the whole thing. And a lot of these systems are incredibly network dependent. Incredibly network dependent. So someday, I was asking this very question actually of one of the guys on my team, and I said, well, what happens when the network is so fast that, it's not a bottleneck anymore? And he said, well, databases will just be bigger and we'll just need more of it anyway. So that's probably true. That's probably true. Okay, so when you do the job right, what you end up with is instead of an IO weight graph like the top one, you end up with a nice graph like the bottom one, where you have a reasonable amount of CPU and it's all productive. That's what you really want to see. And by the way, if you're looking for trouble in your database engines or your environment and you want to predict it before you see that hockey stick kind of curve, what you want to do is look at your IO weight. If you see that start to grow, you know you're going to be seeing serious trouble soon. So it's really good to watch that. All right, so now we've talked about kind of what makes databases slow and what the problems are. So I'm going to just, I have a kind of a pet peeve of mine. How many of you learned data modeling in your career? Okay, that's great. So a lot of people today think that because they're using, let's say, a NoSQL database or something else, that they don't need a data model anymore. And I can tell you that it's actually more important in a NoSQL database than it is in a regular relational database, because at least a relational database helps you a little bit. So anyway, I have this saying, which is that all data is relational. And so what do I mean by that? Well, there's a lot of us here, and we're at one event, right? That's a one-to-many relationship, right? We have a lot of buildings on one street. That's another one-to-many relationship. And if you actually look around the world, I actually think it's a relational world. Now, maybe that's a twisted view, but oh well. But the point is that it's really true that all data is related to some other data, because does it really have any meaning to say that, let's say, the address of this building is 557. Well, 557 what? Right? 557 people, or 557 feet tall, or, oh, it's 557 Broadway. Now it means something because that's related to something else. It's actually what gives the data its meaning, is the relationships. And so it's very, very important. And databases from the very beginning have tried to express those relationships. And so it's kind of interesting that in the history of databases, if you actually look at how a lot of the NoSQL databases work today, so let's say you take an object database, a key value store, and you have a complicated object that has nested fields and things like that inside of it. Aren't those one-to-many relationships that you're managing yourself instead of the engine managing it? It is kind of the same thing. I'm not saying it's a right or wrong thing to do. I think it can work very, very effectively in some cases. My point is, you still have to have those relationships, or the data doesn't mean anything. It's really, really important to look at it that way. Does that make sense? Okay. So it's important that you essentially apply some sort of database modeling technology to whatever kind of engine you're going to use, so that you actually get something that's sensible at the end of the day. Now, it's very interesting. If you've seen these complex objects that you can do in the NoSQL database, they look suspiciously like what we used to call hierarchical data in a non-relational database before relational databases even existed. There was a database in IBM mainframe days called DL1, which was Data Language 1. Who knows about DB2? Heard of it? DB2 got its name from DL1, Data Language 1, and then it changed to DB2. So that was the relational role. And essentially with DL1, it was a hierarchical structure, and you had to set up a record that had all the relationships in it, very, very much like a key value store today. They looked almost the same. But it was very, very difficult to work with, because why? If you wanted to get something lower in that record, you always had to go through that same path. And we have the same problem today. You can see, for instance, if I have a game and I have a player record, a player object, and inside that player object I keep a list of, let's say, the player's top 10 scores or something like that, I can't get to those 10 scores unless I go to the player first. That's the only way I can do it, unless I index them some other way or put them in another structure. And that's very much the way databases work before we have relational databases. So my point is not that you shouldn't use that approach. My point is you need to understand it and see that it's still a data model and it's still basically a structure of relations in a relational database. So the key becomes who manages the relationships. Well, in a relational database, you get a little bit of help. And in an object or key value database or a NoSQL store, it's all up to you. You have to do it yourself. So what does that mean to me is it's even more important to actually understand your data structure in a NoSQL database than it is in a relational database. It's kind of odd to think about it that way, but I've been at events and talked to various people. I remember one guy who said, we started out with a NoSQL database and we got things done so quickly we couldn't believe it. But 3 months later it was such a jam and we couldn't work with it at all. We had to rewrite the whole thing. And that was a production system and it was very painful to do. So it's very important to plan it out and know how you're going to get to your data. All right, so we're talking about database scalability and sharding. And there's two basic approaches in the world to accomplishing sharding. One is what we call black box sharding. And what do we mean by that? Black box sharding means that you have no control as the developer or the DBA over how the sharding is done. The engine is doing it automatically for you, and it's essentially a black box. You can't really control it. The other way is what we call relational sharding, which means that you're actually selectively deciding how to actually shard the data, meaning you're picking the shard key, and you're picking what's going to get sharded together so that you can actually do things efficiently. And I'm going to just show you a little bit about the two approaches. So if you look at black box sharding, essentially what happens is you're just using like a NoSQL store, and you're saying put something based on the key in a certain shard, and then get something by a key from, let's say, another shard. So that's how all the NoSQL stores work. Now this is incredibly simple. Anybody could write this. This is really a piece of cake because why? In a key value store, you only have the key and the value is kind of an opaque object that nobody really knows what's in it. The engine doesn't really know much. It just knows what the key is. So it's very, very simple. And as long as you're reading and writing one key and one object at a time, it works great. It scales very, very well, and it works fine. So this is how Cassandra works, and I could name lots and lots of different engines that work this way. And they're very effective, if your problem is limited to that. When you have more related data with relational sharding, what you want to do is you actually want to have tables or objects that are sharded together. Why? Because if you're looking at, let's say, customer information and you have an order entry system, you'd like to be able to retrieve that customer's orders from one server instead of from multiple servers. You asked about network impact. That's how you can get the network impact to be horrible. If you use a black box approach and something like this, now the customer could be on this shard, the order could be here, the order lines could be here, here, and here. Now all of a sudden you end up looking in more places. And when you look in more places, everything gets slower because it's all network dependent. So that's not a very good way to do it. So that's why we talk about relational sharding, where you're doing things in a more intelligent way and basically putting things together. And so this is what relational sharding looks like. It's basically, again, you're basically doing a select and it figures out where to go, but it can get more than one thing at a time. And I'll show you what that means in a second. So, for example, you can, if you're looking at it as a SQL type thing, you can say that, looking at the query, you can actually see what you're going to shard by. So for instance, if we're sharding by customer ID, we can look at that part of the query and decide where to go. If we're inserting, if we're doing an update, we can look at that key and know how to do it. Yes?
Quick question. Is there a case where the black box sharding will be a better option than the relational one?
Yeah, the question is there an option when black box sharding would be better than a relational one? And the answer is, if it's a key value store, black box is absolutely the way to go. You don't want to have to worry about it in Cassandra where things go. Matter of fact, they tell you you actually can override the settings in Cassandra, I believe, and actually determine more of how the sharding is, but they really recommend you just don't do it. Because the engine can do a great job of that because it's pretty random, right? And that's the way it works. But when you have related data, and you want to get to, well, who needs to bring back lists of related data? Anybody ever need to bring back a list to a screen or something like that? Well, how do you do that if that data is scattered all over the network? It's much more problematic. And what we will talk about at the end is there a way to kind of go closer to black box that make things more flexible and more scalable and efficient like relational query? So anyway, so the basic difference is black box does what we call scatter gather. You're basically scattering the data all over, and when you need to bring back lists of things that are related, you have to go crawl a lot of places and bring it back. And if you look at a lot of the database engines, even the ones that are based on Hadoop especially, those are all parallel, most of them are parallel scanning engines. That's what you have. If you look at Parquet, the way that it works, based on the Google Dremel project, I could just name tons and tons of them. Of course, MapReduce is exactly that way. Well, what are you doing? You're looking at all the data and you're trying to do something with it really, really fast and reduce it down to an answer. And that can be great for some types of analytics queries, but it's not good for real-time systems at all. It's just not going to perform the way you want. Okay, so anyway, so the great news about distributed databases is that they're distributed, right? They're shared netting. They're basically, you have single server, low latency operations that are very, very fast. The bad news about distributed databases is that they're distributed. We have the same problem, right? Because distributed operations are inherently slow. As soon as you have to do a distributed operation across a number of servers, your back-end Bell's law and you have these limitations. That's essentially what's going to happen. There's something in some of the Hadoop systems, you may have heard something called shuffle joins. But that's an even worse problem, which is a distributed join, where now you're joining records from this chart, this one, and trying to put it together. Now all of that traffic is going over the network. And if you try and join 2 tables, let alone 6 or 8, you really can run into trouble very, very quickly. And then I have what I call the ugly of distributed database, which is the really, really worst problems, which is there's this nasty thing called data rebalancing. This is when you have essentially a sharded system, and essentially one gets too full, one chart gets too full, and you have to redistribute things all across your network. It's an incredibly intensive process. It can slow everything down, and it can really cause lots and lots of trouble. And this is just a picture of essentially what happens when you do parallel queries. We have a really highly technical term for this. We call it go fish queries, because it means you don't know where anything is. You have to go find it, go look everywhere. So I have something that I like to call the database sharding endgame. And effectively, the idea is that there's different kinds of shard actions. It doesn't really matter what database you use. They may have different names for these things, but these are pretty much the only things you can do. You can basically have what we call a shard read, which means I'm reading from one shard. That's the fastest thing you can do. You can't do anything faster. The next one is a shard write. That means I'm writing to one single shard. That's the next fastest thing. The next one is a multi-shard read. Again, I called it go fish, which is basically reading from lots of places and aggregating the data or sorting or something like that, doing a join. And then the last one is a multi-shard write, where I'm actually doing a distributed transaction across lots of machines, and that's the absolute worst, and that's what you want to totally avoid. So this is really, like I said, from fastest to slowest. So what you want to do is have things working in the top categories there. So the objective for any sharded environment, and this is what I call the endgame, is essentially you want to have the highest possible percentage of low latency single server operations, which means shard read and shard write. If you have that, you're going to have linear scalability. Your system's going to work great. And you want the fewest possible occurrences of multi-shard read, and definitely try and avoid distributed transactions with multi-shard write. They're typically unavoidable for some percentage, but keep it as just as minimum as you possibly can. And so when you do this, you get great scalability and everything works out fantastically well. So now I want to talk about, we talked earlier on, I mentioned the idea that maybe we're looking at databases the wrong way. And I want to explain what I mean by that. So I know that all of my career I've been looking at databases this way, so this is not unusual, which is basically a database as what I call a static repository. What's a database? It's where you write something to it and you get something out. That's what you want, right? That's the whole goal, the whole thing. So I said, all right. So what happens is when you start an application project, it looks like this, where you write some data and you read some data. The schema is simple. You need one server. It all works fine. And I like to joke, but it works fine for anywhere from a couple of days to a few weeks, depending on how fast your requirements are changing and how fast things are growing in your database. So, but then what happens over time is that the schema gets more complicated because people ask for more features. How many of you have ever worked on a project where they ask for features that you didn't expect? Like every day, right? That's what we do, right? So essentially what happens is the schema gets more complicated. Then what happens is it gets very, very difficult because we have to take that complicated schema and write more complicated code to actually access the data, to read and write it. Very often we have to process the data midstream as well, and so our applications get more complicated. And then a lot of people are finding that because the thing is so slow, and they try and scale it or whatever, they end up having to actually resort to using other database engines besides the one that they started with. So how many of you have more than one type of database engine running in your company? Okay, fair number, right? That's called a polyglot system. Multi-time means multi-language, right? So what happens is now your application has to deal with complicated schemas across multiple engines, not just multiple databases. And if you're scaling, it's hard to show in a picture like this, but if you're scaling, now you have the scaling parameter on that as well. So now add all those things together and you can have a real mess. So I'm working on a project right now with a customer, and they actually have 9 different database engines in one application. That's no lie. That's extreme. It's the most I've ever seen, but it does happen. It does happen. But it was exactly this way. Is they were under a lot of time pressure, and every time they got a feature and they couldn't deliver it, and it wasn't going fast enough, they said, oh, we'll just add this to it. And they kept doing that and doing that and doing that. And in a couple of years, they ended up with 9 different systems, 9 different engines. So it makes it very, very difficult. So basically what I like to say is that databases end up essentially being a graveyard for dead data. That's essentially what we do, right? And it happens more often than you think, especially in older systems. We have a customer right now with a relatively simple application, actually. And that customer we looked at their data model, and they have 500 tables in their data model. And they have it's a small business marketing application. It's pretty simple, really. We looked at it, and I said, what are you doing with 500 tables? And the CEO, who's pretty technical, she told me, she says, well, the system's 10 years old, and she says, we don't know what 400 of them are anymore. So it's very common that there really is a lot of stuff that ends up in databases. It really happens quite a bit. I actually had one project once where I had to get some data out of a system, and the manager delegated that to one of the developers. And it seemed like pretty simple. We just needed to get the data out. It was a mainframe system, but it was a 20-year-old system. And 3 weeks went by, and this developer still hadn't gotten us this report. All we needed was a text file of some fields from the data so that we could do something else with it. So I went to the manager and I said, what's the problem? Why is it taking 3 weeks to just get a simple dump of this, few fields that we require? So she said, I have no idea. So it turned out that she actually wrote the system 20 years earlier herself. And she went and actually investigated the system, and she actually found out that every developer who'd come and worked on that project didn't understand what the one before them did, and they kept adding new ways to do the same things. So they get a new feature and they go, I don't understand what that guy did, so I'm going to just add something else. And so it got so bad that the database was so complicated. She threw up her hands, and she came in over the weekend and she rewrote the whole system. And then we had a report like that. So it's really simple, right? So this is more common than you actually think. And so this is what I mean by looking at databases the wrong way. And I'm just going to give you an example, a simple example of how this happens and how it actually causes confusion and complication. So let's just say we want to make a game. We're going to start a game company, right? Some of these game companies make a lot of money. Sounds like a good business to me. So basically, what do you have in a game? You have players and you have games. That's pretty easy, right? And so typically, you'll have a player game table. Works out great. So we put this together. It's on a single server. We're running away, and people like the game. It's going really, really well. So now what happens is somebody comes from product management or the users or whatever, and they go, can you make the game do something else? So now the game's growing fast, but players say that they want to see the game instances that they played. So they don't just want to see, they want to be able to see that, right? And the game's growing really fast. So what do? Is we basically say, okay, it's growing too fast, it's getting slow. We're going to go ahead and use sharding, and we're going to shard by player. And it's going to work out great because now I can shard by player, and I can also shard the player game table based on the player key. Now those are in the same server. Now I can answer that query just like that. It's going to be really fast, and it's just going to go great, guys. So now we do that, and everything's running fast and fine, and everybody's happy. And then now the game's getting it's getting serious growth. And by the way, I've seen games go from nothing to, I think one game went to 7 million daily active users in 6 months. So When I say fast, it can grow really, really fast. So now they come and they say, now the game is really big, and they go, can you make it do something else? What we want to do is now, we can see the games that we played, but this is a multiplayer game. I want to be able to see the games, I want to see who my competitors are, who am I playing against. Well, we tried to do that, but remember, we started by player ID, and we have that list only by player ID. So guess what? If we want to get that answer, we have to look everywhere, don't we? That becomes a go fish parallel query all of a sudden. And that's not going to work if we have 7 million users a day hitting that thing. No way. So what do? We say, okay, no problem. We're going to take a copy of some of the data, and we're going to shard it by game. And we're going to have another game player table now. It's actually going to be reverse, and now we have kind of two ways to shard the data. And so our application is just going to write to the first one and write to the second one every time somebody does something. How many of you have had to take denormalized data like that and maintain it from your application? Happens all the time, right? It's a very, very common thing. So okay, but we do it, and it's actually working fine. And now the game is really, really good and really, really huge. But they come back and they say, but we're not really making money. And the reason we're not making money is because we only get paid when the users get to the higher levels of the game. And they're not getting there fast enough. We need them to get there faster. So we've got to figure out why they're not getting there faster. And what are they really doing? We don't even really know. And so, by the way, this really happens. So they said, okay, we want to add a new requirement, which is now we want to track every click that the user makes in the game. 7 million users a day, every click. So that we can actually track what's going on, so that we can actually see what they're doing, so we can figure out how to make it so they like the game better, and we'll get to the parts that actually pay us. And that's how it works. And all the big game companies, the really big ones, they work very, very hard on this kind of problem. So now, all of a sudden, we went from a lot of data with 7 million users to an unbelievable amount of data. Now we have a huge big data problem. So, and then after all that, they say, well, now the players want to see a leaderboard. I mean, we want to know who the top 100 players are. So we go, gosh, now we have to add that somehow. So we go ahead and figure that out. Maybe we're going to implement that with Redis or something like that. So we do it in memory because we can't do it any other way. And then after that, they go, well, we can show them a leaderboard for all players. But now the players are telling us that they want to be in teams. And now they want a leaderboard for every team. All of those teams could be geographically based. It could be all the people in New York or all the people in Los Angeles or whatever. So they can put it together any way they want. So this might seem far-fetched, but I told you about Big Door early on. Big Door has millions of leaderboards because they let any of their customers break it down by any type of thing that they want. So fantasy football leagues, all those kinds of things can have their own types of leaderboards in those systems. So this is how you end up with this mess. I hope I made the point that this is how these systems evolve over time into something that's very, very complicated. And you get this basically very complicated static picture, complicated queries, and everything else. So I'm hoping there's a better way, because I have struggled with this problem all my career, and I really don't like it. I really, as an application developer, having to manage these systems and all the other jobs I've done, it's really not a lot of fun. So we basically said, is there a way to have an Agile view of big data that will actually let us respond to application requirements in a better way that will still let us scale and will make things much, much easier to work with? And we basically flipped the problem. And what we found was, if we quit looking at a database as a static repository, and we start looking at our data as a real-time stream and working with that stream, all of a sudden we can solve these problems very, very quickly and much, much easier. And I'm going to show you how this actually works with what we call an Agile big data approach. So basically, an Agile view for big data. Essentially, wouldn't it be nice if we could actually work with data as a continuous stream, and we basically could support what we call views of the data that actually match what we need to do in the actual application. So for instance, if I want to see the list of players by game, or I want to see it by player, those are just two views of the same data, and I can do that. I can shard them the way that I want. I can make it very, very scalable. And what if we could maintain integrity even across multiple types of database engines? And we could make that easy so that the and the application developer doesn't have to worry about any of that stuff. Wouldn't that be nice, right? And we could basically keep the complicated data structures completely isolated from the application, so the application developer can work on what? Features. That's where we make our money, is from the features, not from developers trying to constantly tackle these database problems. And basically get things back to simple read and writes from the application. So those are our goals. And so what we basically came up with was a very simple way to look at this. And we basically said an Agile Big Data view of the system is basically a set of streams and views. And what do we mean by that? Streams are where we manipulate the data in a real-time stream. And whenever we want to query that data, we store it in a view that's exactly the structure that we want. That's how it works. And we can go through multiple steps to do that. So the V's are the views and the S's are the streams. And that's how we put it together. And so this has been incredibly effective. Essentially, what we do with this is we basically create distributed views that are eventually consistent. That's really the key of how we do it. And we basically do that by managing a polyglot DBMS environment, meaning we have multiple database entries. And so instead of looking at your database as a static repository, look at it as a real-time stream and a series of views. And each view can be essentially an isolated part of your schema that matches that one requirement. It makes it easier to understand, it makes it easier to document. Even if the system's around for many, many years, you can keep track of what those views do, who created them, why they created them, and how they're used. It's very easy because they're all isolated and they're distributed according to what they need to do, not by some other logic. So that's the way it's set up. So before I go on, any questions on this concept? Because I'm going to talk more about it. Yes?
So how do you manage the views? Because eventually you'll get so many of those views that you won't know where what is.
Yes, that's a good question. So how do you manage the views? Because eventually you're going to get a lot of views. We basically have found that in working with this, and by the way, this is a pretty new concept that we're working with. This is what we're coming out with in some of our new technology, but you can apply it yourself anyway. But essentially, we want to make it very easy to, let's say, have 1,000 views and have that not be a problem. Because it's still only 1,000 things, and each one has a specific purpose. So you can easily document that view and say, this view is to support that kind of query in the game or something like that. It becomes much easier to look at it. Whereas if you had 1,000 tables in the database, and you were trying to figure out what these 5 tables do and how they're connected to the rest, it's a much more difficult problem. So, yes?
So if you add a new view, do you have to like replay the entire stream from time immemorial and repopulate it? That's how you do it?
That's a good question. So if you're going to add a view, do you have to replay the entire data set from the beginning? And so the answer is we basically have made it to where you can create a new view, and you can say, I only care about starting it from right now, in which case you don't replay everything. You can say, I only care about starting it from a month ago, or you can say, I do want to go back to the beginning of time. So if we make that a choice, what we found in this case is most often when people create new views, they really don't care about historical anything, or not much. Yes?
So a view is a single database?
A view is essentially yes, it's a single instance. If you think of it like a distributed table, it's distributed the way that you want. And that view could be across 100 servers, or it could be just on one. It just depends how big it is and what you're doing. Right? It could be summary data, it could be detailed data, it could be data in a different way, it could be indexed a different way, it could be 4 or 5 tables together. It could be an object store, it could be anything you want, a column store.
And if you have 1,000 views, that means you're saving to 1,000 different places every day?
Yes, so the question is if you have 1,000 views, you're saving to 1,000 different places. If those 1,000 views are all based on the same data, which is not very realistic, right? So we've seen it be a limited number on a certain set of core data. But eventually, yes. Eventually, yes. And we've even seen people have needs to, let's say, create views temporarily and then get rid of them. They just needed it for some temporary purpose. Yes, you had a question? Yes.
Yeah, how is it different from the 500 different tables?
Yes, how is it different from the 500 different tables? It is similar in that respect, except for you can manage and shard 500 tables. I can tell you from hard-won experience, because of our prior product, that basically when we did this, as soon as we sharded the database this way, users said they couldn't do this type of job, just like I showed you with the game. Those were real examples, by the way.
Well, I'm really not talking about the problems of sharding, but like managing it.
Yes.
400 of them, nobody would remember what they do, what they're for, and
Yes.
whether they need them.
You do still have to keep, some sort of documentation of record so that you know if they're using them or not using them. But you also can get statistics now much more easily because you can see what's getting hit and not getting hit. So it just does become easier. Look, it doesn't totally magic make the problem go away in a complicated system, but it does make it much more manageable. We can much more manageable. So, yes.
You spoke about there are multiple database management systems that is involved in the system, and then is there a layer sitting on top to manage all the connections? And what is that?
Yeah, so the idea is if you have multiple database management systems, is there a layer sitting on top of that? Well, our technology that's coming out soon is going to manage that. It's going to be one way to do this. But you could do it yourself. It's not that hard to see how you could actually put something together like this with some sort of middle layer that's actually managing it as well. Yes, I'll take a couple more and then I'll wrap it up.
You need some sort of other database that's sharded only one single way to store all of the data. I mean, if you have some kind of accountability that you have to be able to account for after the fact, where you need to, somebody can come and ask a question that you don't know what type of question it's going to be, but you need to answer that at some point in the future. How do you deal with that? Just having something that maybe is not a real-time query that you wouldn't have to do in real time, but would require you to have.
That gets a little more involved, that answer, but we do have an answer for it, and I can show it to you. I can talk to you afterwards if you like.
Sure.
But I'm going to also talk about some more details about this in a second, and that'll hopefully help a little bit. Okay, all right, so let me go on, and this may answer some more of the questions. So basically, one thing is we said, all right, what makes a view an ideal view? What makes a view an ideal view? And so we basically said that we came up with if it has the right schema, and the right engine, the right database engine, and the right partitioning strategy, that makes a perfect view for an application, for a given requirement of an application. Now this came from some work I did many, many years ago. We had a relational database and we were pumping a lot of data into it. And the users needed to run queries on this data to be able to do financial calculations. And those queries were taking like between 20 minutes and an hour. And they had to do hundreds of these queries a day because it was essentially for a bidding system, and if they didn't respond quickly enough, they were going to lose business. So it was really a big problem. And so finally we got frustrated, and we had a good C developer on our team, and I said, can you take that data and put it in some other format on disk and actually write a C program that will be faster? And at the time I was naive enough to think that it was because C was faster, but it wasn't really what happened. But what he did was he was able to structure the data to answer that query in a better way, and he dumped the data out of the database, put it in there, and all of a sudden he could do the same queries in a few seconds that were taking minutes and hours to do. And we were able to meet that requirement. And had I been smart at the time, I would have called him MapReduce and made a fortune. But anyway, it was essentially that same type of technique. But the point is, I learned something from that was if you get the data in exactly the right structure with exactly the right access approach to that data, magic happens because everything is simple and things go really, really fast all of a sudden. So it's amazing. So do you need an in-memory SQL database? Do you need a key value store for that? Do you need a column structure? Do you need a relational database? Do you need, I could just list them off, right? So if you get the exact right approach to that problem, and you get the exact right schema, all of a sudden it's really magic how fast things go, and also how easy it is, because now you're not struggling with all these performance problems because the data will naturally work the way you want it to work for that problem that you're trying to solve. And so that's really what we put together. And so I have what I call the characteristics of an Agile big data infrastructure. We won't go through all these, but basically I could send you an email with them all if you want to study it too. But essentially, data should be processed as a real-time dynamic stream. The input should be simple. Views are the core construct of this whole thing. The view schema should exactly match application needs. You want them to really match what you're doing. The engine should be pluggable, so you can use whatever engine you want for a given job, supporting a polyglot environment. The view queries should be really fast and easy because the views are already in the form that you need for those queries. The streams must support transactions. Somebody asked about reliability, so that's exactly how. Right? So if everything is transactional all the way through the environment, that really helps. They need to auto-scale. So somebody else said, well, when is, I think you asked, when is black box sharding better? Well, we can come a lot closer to relational advantages with black box sharding this way. because it's really easy to shard one view. It's really hard to shard a whole database. Okay. So anyway, some other things here too should be easy to manage, and also interoperate with what you have now. You shouldn't have to start over. That's also another drawback of these things, is having to start over. So here's an example that we put together with our product. I'm just going to explain it briefly and just show you how it works. But basically, we work a lot with Google and in the Google Cloud, and they came to us with a use case, and they said, what if somebody had a MySQL database that's remote to our cloud, that's running somewhere else in their own data center, let's say, and they have a MySQL order entry system. And when an order is shipped, they want to move that data into BigQuery in Google Cloud, but only when an order is shipped. So what we were able to do is we were able to take the MySQL transaction log and turn that into a stream, a MySQL binary log, for any of you who work with MySQL. We turned it into a binary stream, and whenever we saw a shipped order come through that stream, we actually went and retrieved the order and the order lines, which was very, very fast, because those are real easy index queries. We then basically streamed the data over the wide area network from the internet to Google's cloud. And in Google's cloud, we did two things. We basically, on the bottom, we had one view that was basically a summary of statistics by product. So we said how many, what's the total of orders by product? Every minute, every hour, every day, something like that. So that data was pre-summarized. So that was an aggregate view, which makes the aggregate queries really, really fast. Probably most of you have seen that aggregate queries are often very painful in a regular database, so this made it very, very quick to do. It's kind of like MapReduce on the fly. And then we basically said, okay, take the data also at the same time, and in parallel, stream it into BigQuery so that any type of detailed analytics query can be done on the fly. Because BigQuery is an awesome data warehouse type infrastructure that you can do any query on. So anyway, we were able to put this together in a very, very short amount of time and actually get a demo working and show how this would actually flow. It was really pretty easy. It was amazing how many problems we solved with just a few views and a couple of streams. It was really pretty easy to put together. So I guess the thing that I like about this approach is that now when we talk to somebody about a problem and we just look at it this way, what used to take us many, many meetings and sometimes weeks of working back and forth to figure out what the exact right solution was, now we can do it in a few minutes or an hour. We can actually usually come up with the concepts of what we need to do very, very fast. Only because we start looking at the data as a stream, we say, oh, if you need it this way, that's one view. If you need it that way, that's another view. That one has to be sharded this way. That one has to be sharded this way. We want that kind of engine here. We want that kind of engine there. Boom, we're done. It's a very, very quick and easy way to work. Yes?
So you wouldn't have, basically you're bypassing the whole, here's my whole big picture of all my data, right? You don't even care about that. You're just saying, this is how I have to look at this, that's how I have to look at that.
That's right. That's right. And this is particularly good if you have an existing database like a MySQL database, where you're trying to run queries on it, but it's really inherently bad. Like it's fine for your order entry system, but it just can't do the rest of the job you're trying to do. Now you can just offload that job into a couple other views and you keep your database just the way it is and nothing changes. It's really, really nice. Okay. Is the question there? Yes.
How are you ingesting the data into your cloud?
So we basically, the question is, how are we ingesting the data? So we basically said we can eventually, not yet, but we can eventually make a string out of almost anything. So you can use a client. You can see we have something called Agile client here. So you can just use that, and we basically, from just a regular application, we can turn that into a stream. We can do it from a MySQL transaction log. We can do it from files. We can do it from, eventually other types of database engines. A lot of database engines have transaction log type capabilities. We can take feeds from that. So we should be able to do it from almost anything. In other words, if you look at all data, at some point it's streaming somewhere. And if we can tap into that.
Is that like Flume or?
It's similar to Flume, yes. It's a similar type of approach.
Somebody asked me, streaming assumes that the data is like whatever is happening now. But what if you want to look at historical data?
Yes. So the question is, what if you want to look at historical data, and you do have that problem if you want to build a view of historical data? Well, you have a couple of choices. If you want to build a view for really fast access of historical data, you are going to have to go back and rebuild a view from that history, right? So there needs to be an efficient way to do that. We think we have some pretty good answers for that. But the other is if you really do want to do any kind of ad hoc query to historical data, you should use something like BigQuery. So notice that we didn't say not to do something like that. Right? BigQuery can handle terabytes and terabytes and terabytes of data, I think even petabytes, for a very reasonable price, and you can basically ask any kind of question in a very reasonable amount of time. They'll basically can partition a query across 1,000 servers, and you won't even know it's happening. Yes?
And a similar question, I was going to use the word archiving. Do you have any concept of archiving in your model?
What is it?
Archiving the data.
Oh, archiving the data. So the question is, what about archiving? And the answer is yes. We can archive data, and we basically can store data easily somewhere else and then be able to reload it if we want to.
So meaning we use those views on the archive data?
Yes. Yes. We can basically build a view from anything we could turn into a stream. We can build into a view. Right? And there is a time lag if you're building a historical view, obviously. Right? But once it's going, then it stays current, and if you don't need it anymore, you can throw it away. And by the way, a lot of you asked about, well, what's the difference if you have 500 views or 500 tables? It's a lot easier to get rid of one view without breaking the rest of your application. Right? Try and take out one table from a very complicated database structure. It's very difficult because you don't know what's really going on there.
So you never build views on top of views?
The question is, do you build views on top of views? You can actually stream them, so you could have a view at one interim stage and another interim stage. But even if you do that, you can see how they're interacting.
How is your approach different from CQRS?
Say again?
From CQRS, how is your approach different, much different?
And we could take that offline. That's not something I'm totally familiar with, but I'm happy to try and answer it. All right? Cool. Yes?
Would the data persist in the view or just a snapshot?
Our definition of a view is that the view is a persistent queryable representation of the data. That's what we call it, right? But they could just be in memory also, if you have enough in memory to do it, right? You could just use an in-memory database. There's all kinds of approaches you can do.
So is the stream just getting the data itself and manipulating it for the data?
Exactly. The stream basically takes the data and manipulates the data in the form that it needs to be manipulated, and if it doesn't need an in-memory representation, you can just query that. Or you could do other kinds of things. You could say, based on what's happening, I want to send an email to somebody to alert them of some condition. Or give the user an award or whatever else you wanted to do. Yes?
What about if I have a view that's defined with certain parameters, like maybe geographical parameters, and I want to instantiate for a limited period of time one of these views with a different geographical parameters? That's something I could do?
Yeah, the question is if you had certain parameters on one view and you want to instantiate another view for a certain period of time based on a different set of parameters, of course you can do that. Again, depending on how much history, you have to rebuild it, from that point in time. But you can do all that while the infrastructure is running. You don't have to stop it.
Okay, but each view is connected to its own database, whatever type of database that is. Would I have to reinstantiate the database, or can multiple views be running on one backend?
Well, if I get my way, it'll all be automatic anyway, so won't matter.
I hope you get your way.
Yeah.
Are your views live or static? Like,
The
have to be rebuilt?
Yeah, are the views live or static? And so the answer is the views are live. Right? The views are live. Even with, that's a good question actually. With BigQuery, it used to be that you could only kind of batch data periodically into it, but now they made it to where you can do real-time streaming. So it's a little bit behind, but it keeps up. It's pretty amazing actually what we're able to do here. Yes?
One last question, this is kind of a mean one, but when won't this work? Can you imagine a scenario where this would not be very effective?
Yeah, I'm sure the question is when won't this work? And I'm sure there are things we're going to run into where it won't be the easiest or the best answer. But I can tell you if you have, well, I'll take one that I believe is the case, right? If you really wanted to do this with a real-time trading system or something where, microseconds count, it's not so good, right? Because clearly, these views are adding latency. The whole approach adds latency. But most of the time, in the projects we've looked at, the really low latency stuff happens at the kind of the front of the cycle and not so much at the back. So most of the time it's kind of been okay. But I'm sure that there are cases where you can't afford that delay. Yes?
So just going
back to the previous example, you're talking about the gaming something, right?
Yes.
And if you're trying to build these top 5, top 10, 100, each of the groups that are there, you need the current data which would be in your stream, but then you still need to go back to your historical data to do the analysis and bring the people. So how you would still be doing your query against this view and going back to historical view that would be sharded still, and you would still have issues, right?
Well, the question is, if you had to do that, you had to build a view all the way from the beginning of time, it's going to take however long that takes to do it. That's true. And sometimes if we're working with an upstream database, it might mean that we have to run some big giant nasty query on that database. We might run it from a copy of the database so that we don't slow down the production one. So there's going to be some overhead in actually getting that going. But we can do it in ways that shouldn't slow down the production system. That's the key. Yes?
So the stream is basically a copy of the data from the original MySQL or Oracle, whatever it is, copied into a stream. And then there's a view that looks just at that particular stream.
That's right. The stream is basically we watch the data as it's happening, or historically, and we basically pump that into the stream, and then we manipulate the views on the fly.
So in other words, it's only for reads, really, as well. You use it for writing or
Oh, I see. You mean, could you write to streams? Well, effectively, the streams and the views are written to, just by fact of writing to anything in the system. So you may be writing to the front end, and as you're adding new data, you're still writing to all the views. So it is really a real-time system.
So you write to the MySQL database and then come back up the stream.
That's right. That's right. But this case is MySQL, right? So this is really only one case. Like I said, you could use our client, and it could really be your application. So it could be your whole database, or it could be coming from files and system data. I mean, there's just so many different use cases that we've seen that this could support. So yeah, I have just enough time for a couple more questions, but yes.
Are the views created through MapReduce? How are the views created?
So are the views created through MapReduce? It is the streaming process when we do aggregate views, which is a very common use case, by the way. Most people start with us because they need a real-time dashboard or something like that, and so they want aggregate views like this stats by product. That's what that is. So that is kind of like a streaming MapReduce. It's exactly that kind of thing. So we're saying, okay, a minute went by. We're supposed to do it every minute. Now we create a record from view. That's a summary of the last minute.
How do you deal with the update? It says somebody you stream over, but there are subsequent updated prior value.
Yes, so how do we deal with updates? Essentially, updates are, we basically make another version of the record, is how we do it. So we actually have version of posting. So anyway, I hope I got you thinking, though. That was my intent, is to get everybody looking at this as a concept that you could apply. So I have, I was going to take questions, but I think we already took them. So, but what I did want to say, though, is if any of you would like a copy of my book, we're trying to get the rankings, I'll be candid, we're trying to get the rankings at Amazon. No, I don't want you to buy it. We're trying to get the rankings at Amazon higher. So if you agree to write a review on the book, we'll give you a free copy of the book. All you have to do is you have to email me at Cory@CodeFutures.com, and I'll be happy to do that. If you have any other questions or anything like that we can't cover tonight, feel free to email me as well.
We have time for about 2 more questions. Before we do that, I just want to give a great big round of applause to Cory Isaacson. By the way, if people don't get into those 2 questions, Cory will be here for one-on-one questions afterwards. So who wants to fire one out? Hands? Right there in the back.
Don't you still have the same problem with scaling out your record, your source database of truth, in that case MySQL? And you'll have less tables because you push on one of that aggregated logic out to the view. You still have that problem with your source database now.
Yeah, the question is you still could have the scaling problem in your source database, but it's a lot simpler. If all you're doing is writing data, it's much, much easier to figure that out. Much, much easier. Yes?
It's very similar to like using varnish or something like that for paint. We're basically aggregating compile, version, view, instead of return back.
That's right. That's right. A good way to summarize this really is we've been denormalizing data for years, right? If you think about an index in the database, what's an index? It's a copy of part of the database in a specialized format.
It's
the same basic idea, but we said, why don't we make that the thing instead of the exception? That really was the idea.
All right. Cory will be here for one-on-one questions. I'd like to ask everybody who's took photographs, post them to the meetup page. Everyone who's a meetup member has the access to view that. Just go to the meetup site and you'll just follow the instructions. You can just upload your images. Thank you all for coming. Thank you, Cory Isaacson.
Thank you.